All right, so this is how derivatives affect the shape of a graph. Also known as curve sketching. All right, so it's not too many slides that we have to get through. It's just these examples. We're going to be dissecting every important characteristic about a curve, so they take a little while to do. First thing, the ID test, or the increasing decreasing test. And this is just what the first derivative tells us about the original function. And it says if f prime is greater than 0 on an interval, then the original function f must be increasing on that interval. And so hopefully that's pretty intuitive, right? So if f prime is positive, that means the slope of the curve has to be positive. So you can see on this interval from a to b, these are all positive slopes. Notice what the curve is doing. It's doing what we call increasing, right? Which means as we move to the right on the x-axis, it goes up. The opposite, if f prime is less than 0 on an interval, then the original function is decreasing. So slopes that are negative are going down towards the right, like this. And that tells us that the original function, the blue curve, must be decreasing on that interval from B to C. And then you can see again, we got positive slopes over here. So f prime is greater than 0, so the original curve is increasing on that interval. All right. Well, help me out in the chat. Whoops. Shoot. Come on, catch up, computer. Bring it back. What is happening at the transition points when the curve changes from increasing to decreasing? Like at point A, or sorry, at point B, the curve changes from increasing to decreasing, so the derivatives change sign. What important characteristic does that function have at point B? Number one, f prime equals 0. Yes, that's a critical value. So the derivative is 0, but the original function, what's this point? The blue function, what's going on at point B? What do we call that? It's a local max. That's exactly right. It's an extreme value, a local max in that case. Awesome, thank you, Olivia. So yeah, two important distinctions. The derivative is 0 there, it's a critical value, and it's a local max. Same idea here. My derivative changes sign from negative to positive. The derivative at point C is 0, and point C itself is a local min. All right, so first, let's do an example. We're going to look at this function. We're going to find where it's increasing and decreasing. So to do that, we want to know about the sign of its derivative. Where is its derivative positive? Where is its derivative negative? So let's take its derivative. So f prime is, what, 12x cubed minus 12x squared minus 24x. Well, if I want to know where its derivative is positive or negative, let's first set it equal to 0. That's what separates positive numbers from negative numbers, right? So set it equal to 0, let's solve. All right, well, I can divide 12 out from both sides. Get x cubed minus x squared minus 2x is 0. I can factor out an x. And then I can factor that polynomial. So that's x minus 2 times x plus 1. So basically I get 3 critical values here. I get x equals -1, I get 0, and I get 2. All right. So I'm going to draw a number line. I'm going to put those critical numbers on the number line. So -1, 0, and 2. And I'm going to look at my derivative on that number line. I know that my derivative is 0 at those 3 points. So in between those 3 points, it has to be either negative or positive, which will tell us if the original function is increasing or decreasing. And so we'll just test values on those intervals. So I don't know, what if I test -2? And I want to test it in the derivative. So what's f prime at -2? And I don't so much care about what the value is. I know that it's either going to be positive or negative, and that's all that I care about knowing, right? So I think it's easiest if I just look at this factored form. You can do that pretty quickly. Because I can go, okay, x is -2. So this is going to be -2 minus 2. This is going to be -2 plus 1. This is going to be negative. So a negative times a negative times a negative is a negative, right? So I know that this is going to be less than 0. All right, so I know that f prime is negative on this interval. All right, let's choose another value here. So like negative, maybe -0.5. So what's f prime of -0.5? Well, again, if I look on at my factored form, that would be negative times -0.5 minus 2 is negative. -0.5 plus 1, though, is positive, right? So negative times a negative times a positive, that's positive. That's greater than 0. And then let's choose 1 on this interval, maybe 1. So what's f prime at 1? All right, let's test these again. So if I plug in 1 positive, this is going to be negative, this is going to be positive. Positive times positive is negative. So less than 0. All right, so sorry, positive on that interval, negative on this interval. Last one, let's choose something over here, maybe 3. So f prime at 3. All right, so x would be positive. This is positive. This is positive. Positive times positive times positive is positive. So greater than 0. All right. So my derivative, you can see what intervals it's negative on and what intervals it's positive on. And remember what that tells us. That tells us where the original function is increasing or decreasing. So when f prime is positive, f is increasing. When f prime is negative, f is decreasing. So I'm going to go label my answers now. So f increases on 2 intervals. -1 to 0 and on 2 to infinity. Whoa, that is a bad infinity. Let's try again. All right, acceptable. And f decreases on -infinity to -1 and 0 to 2. All right, there's our answer. Any questions? Okay, great. So now we know how to analyze where a function is increasing or decreasing. So that's going to help us sketch. So let's talk about the first derivative test. As Olivia pointed out to us, when a function changes from increasing to decreasing, it has a critical value, and that critical value is either a local maximum or a local minimum. So we can use what I'm going to call the first derivative test to find where there are local maxima or minima. So let's break this down. If f prime changes from positive to negative at c, so that's this first case in the upper left. So we go from positive slopes to negative slopes at a critical value c, then that critical value must be the location of a local maximum. If the derivative changes from negative to positive at a critical value c, so my derivatives go from negative slope to positive slope, then c must be the location of a local minimum. And then finally, if there is no change in sign for f prime for the derivative at c, so let's say we have a critical value. We have a place where the derivative is 0 like this, but we do that little number line test that I did on the previous page, and let's say there is no change in sign of the derivative. So it goes from positive to 0 to positive. Then there is no maximum or minimum at c. Same idea if it goes from negative to 0 to negative. Then there is no maximum or minimum at that critical value c. So we're going to go back to the example we just did, and now we're actually going to find the local minimum and maximum values of the function f in example 1. So I want to be really precise about the wording here. Remember I said the location is an x value, but the value is a y value. So if they're asking us for the local minimum and maximum values, they want the y values. You can always be safe and just give the full coordinate. All right, we've already done most of the work here. So if I go back, I've already found all my critical values, right? My 3 critical values are at negative 1, 0, and 2. That's where the derivative is 0. And then I've already evaluated whether the derivative is positive or negative on each sort of sub-interval. And so now I just need to see, okay, where do the maximums and minimums occur? And that's using the first derivative test. So we know if the derivative changes from positive to negative, it's a local max. Negative to positive, it's a local min. And if it doesn't change sign at the critical value, it's neither. So I'm going to ask for some help in the chat so that I know you're alive out there. What's going on at negative 1? Is there going to be a maximum at this location, a minimum, or neither? So my derivative is going from negative to positive, which means the slope of my original function has to be going from negative slopes to positive slopes. So there must be a local minimum. I agree with you. All right, so this is the location of a local minimum. So then if I want the y value of the local minimum, I'm just going to plug it into my function, right? All right, so I just need f of negative 1. All right, well, I mean, I'm sure you guys can do this in your head. I'm always a fan of, if it's available, use the technology to reduce clerical errors. So I'm just going to pop that function into my calculator, because we're going to have to do this a few more times anyway. So what is that function? All right, so the original function, which is what we're trying to get the y value of right now, is 3x to the fourth minus 4x cubed plus 12x squared and then minus 5. And then I'll just use my table to evaluate what's going on at -1. All right, so my y value is 14. All right, so that is a local min. All right, let's look at our other critical values. What's going on at 0? Local min, local max, or neither? Whoa, I raised too much. There we go. Good, thanks, Ian. Yeah, I agree. So local max, my slopes go from positive slope to negative. So my function must go from increasing to decreasing. So there must be a local max at that point at 0. So I want to find f of 0. Just go back to my calculator, plug in 0. So I already put my function in here, and I get -5. That's a local max. All right, finally, let's go back to this. What's going on at 2? Last critical value. So last location where there could possibly be some local extreme behavior. Min, max, or neither? Good, I agree with you guys. Local min. So slopes go from negative to positive. So the original function must go from decreasing then to increasing. So there has to be a local minimum at 2. So I just want to find that local minimum. F of 2 equals what? $59. Whoa, way up there. But still a local min. Just make sure I typed that in correctly. 3x to the fourth minus 4x cubed minus 12x squared minus 5. Yeah, that's correct. Okay. So there we go. We found all local minimum and maximum values of the function. All right. So the derivative g prime of x in this case is just going to be 1, whoops, not plus, equals 1 plus 2 cosine x. And so the first thing we want to do is find critical values, so set that equal to 0 and solve it. So 2 cosine x is -1, and cosine x is -1/2. All right, and so this one we kind of have to do by inspection, right? So it's trig. Anytime you're trying to solve a trig equation like this, it's going to have to come from a special type of angle, either a quadrantal angle, so one of the quadrants, so it's like 0, pi over 2, pi, 3 pi over 2, or 2 pi, or it'll come from a special triangle angle. And in this case, the only special triangle that can possibly give us a ratio of 1/2 is a 30, 60, 90 triangle. So let's remind you of what the ratios on the sides are on the 30, 60, 90. So it goes 1, 2, rad 3. The 1 is across from the 30, the 2 is the hypotenuse, and the rad 3 is across from the 60. So I want cosine to have a ratio of 1/2. I know it's negative 1/2, but that's just going to depend on what quadrant we're in. So I'm just trying to figure out what's the right reference angle right now. So cosine, remember, is adjacent over hypotenuse. Right? And so I want adjacent over hypotenuse to give me a ratio of 1/2. So that's going to be that 60-degree angle because 1 is adjacent and 2 is the hypotenuse. So basically what I found is that 60 is going to be our reference angle. And now I'm going to look at this now in the context of the coordinate plane. All right. And so where could cosine be negative? So there are little like acronyms that you can remember to help you remember what trig functions are positive and what quadrants. You might remember this from Ken's class, but it's all students take calculus. So that just tells me what trig functions are positive in what quadrants. So for example, in the first quadrant, all trig functions are positive. In the second quadrant, sine is positive, everything else is negative. In the third, tangent's positive, everything else is negative. In the fourth, cosine's positive, everything else is negative. All right, so I want cosine to be negative. So I'm going to be looking in quadrants 2 and 3. And so I have my reference angle needs to be 60 degrees. I just need to figure out what my true angle is. So here we go. I'll draw a triangle in this quadrant. This needs to be a 60-degree angle so that when I make a triangle out of it, I have that 30, 60, 90 triangle where this side would be the rad 3, this would be 2, this would be 1. But if you consider that we're in the coordinate plane, so this is y and this is x, notice that that's the negative side of the x-axis, so that's actually -1. And then my cosine of that angle becomes -1/2, which is what we want. All right. I've been talking a lot, and I've been talking a lot of trig, which tends to send students off into not paying attention. So that I know you're paying attention, in the chat, what's the true angle? My reference angle there is 60, but if I'm measuring from there, what's the true angle? Yeah, 120. Good. So full or a half rotation is 180. So minus the 60, that's 120. I agree with you guys. Thank you. But last thing, we only want our answers in radians. So yes, this would give me one solution of x equals 120. But what's 120 in radians? Well, just multiply by pi over 180 and reduce. So I can divide 60 out of both of those. And that would become 2 pi over 3. Awesome. All right, so one solution is x equals 2 pi over 3. I'm going to have one more in the third quadrant, so let's draw that one in. So now I have a triangle in the third quadrant. This reference angle is still 60, and I still get the -1/2. All right, so what's the true angle now? What's this angle? Whoop. There to there. $240. Good, just 60 plus 120. So then 240, let's convert that to radians. 240 is Divide both of those by 60, you're going to get what? 4 pi over 3. Okay, we found the critical values. That was a lot, but we did it. They're 2 pi over 3 and they're 4 pi over 3. So we have 2 critical values. But this is asking us to find the local max and min. So we're going to do what we did before. Let's put those on a number line. What we want to look at is the values of G prime in between those critical values. So we'll just choose a value from each piece of this interval to test in G prime. So like on the left-hand side, I could choose 0. What's G prime of 0? Well, that's 1 plus 2 times cosine of 0. Cosine of 0 is 1. So that's positive, right? And again, all I really care about is whether I'm getting back a positive or a negative. So you could use your calculator on this. I don't care what the value is at this point. I just care whether it's positive or negative. All right. Well, I need a number on this interval. Can you guys give me a number in between 2 pi over 3 and 4 pi over 3 to test? What's a number that's between 2 pi over 3 and 4 pi over 3? Pi, good. 3 pi over 3, right? So let's test pi. So G prime of pi. Again, you could pop this into your calculator. It's 1 plus 2 times cosine of pi. Cosine of pi is 0. So it's 1. So it's still greater than 0. So still positive. And then 4 pi over 3. Something after that, maybe 2 pi. Give me 1 second. Okay. Yeah, I still get a positive value on this interval, right? So maybe a little unsatisfying in terms of we didn't find a local maxima or minima, but that's because there aren't any for that function, right? There are absolute maxima and minima, and those occur at the endpoints, right? So you're going to have your absolute minimum at 0, on that interval and your absolute maximum at 2 pi. You can kind of see that here. So 0, comma f of 0. There's my absolute minimum on that interval. And then 2 pi f of 2 pi. There's my absolute maximum on that interval, since it just continually increases. All right. So that's still a point of interest to us. That critical value right here. Because there's still some behavior that we want to know about. And so what you'll notice here is the graph seems to be kind of cupping downwards until we get to that flat point. And then it begins cupping upwards after that. No, that has a special name. That's called concavity. So, concavity is this: if a graph lies on top of or above all of its tangents, like this. So if I draw tangents, they would fall below the graph. The graph is considered concave up. And if a graph lies below its tangents, that graph is considered concave down. So what we can see is that we have an increasing slope here. So the slope is increasing. Which means that the derivative is increasing. Well, we can tell if a function is increasing or decreasing by looking at its derivative, right? Like f prime tells us about where f increases. So if f prime is positive, then f is increasing. Now I want to know when f prime is increasing. So I'm going to look to f double prime. If f double prime is positive, that's going to tell me that f prime is increasing. And likewise, if f double prime is negative, that'll tell me about if f prime is decreasing. Whoops, that's not how you spell that. So it's actually the second derivative that tells you about concavity. And so here you can see that the slopes are decreasing, right? They're getting flatter. So that means the derivative is decreasing. So that means that the second derivative should be negative. All right. And this just tells you, so when we talk about concavity, we talk about intervals of concavity. Oh, Audrey, increasing equals concave upward. F prime increasing means concave up. So f double prime being positive, yes, means concave up. F double prime being negative means concave down. All right. So you can see this little diagram at the bottom. This shows you a function with various concavities. So from A to B, we have an interval of concave down. So concave down, from B to C, concave up, from C to D, concave down, from D to E, concave up, and so on and so forth, right? And so there's a point of interest when we change concavity. So that point, capital B, is the point at which it changes from concave down to concave up. That has a special name. It's called an inflection point. So whenever you have a change in concavity, you have an inflection point. So an inflection point, there isn't necessarily a maximum or a minimum, but there is a change in concavity. And that's what's going on in what we found here, right? So here at this point, we do have inflection. It's not a maximum or a minimum, but it is a change. You can see the graph goes from concave down to concave up at that point. Whoops. All right. So it's the second derivative that tells us about concavity. And so that brings us to the concavity test, right? If the second derivative is positive for all x on an interval, then the graph is concave up on that interval. If it's negative for all x in an interval, then the graph is concave down on that interval. And then we have another way of finding local maxima and minima. So we talked about the first derivative test, which is just looking to see where the function changes from increasing to decreasing or from decreasing to increasing, and that can find us a local maxima or minima. Another way to do it that's sometimes faster, because you can use your calculator oftentimes to do this, is the second derivative test. So if you have f prime equal to 0, so critical value, remember we call that a critical number, at c, and you know that the second derivative is positive, that means the graph must be concave up, right? Because that's what the second derivative tells us. So this is telling us concave up. So if you have a critical value, and at that value the graph is concave up, then there exists a local minimum at c. So you can kind of see that here. So critical value, and you know your graph is concave up. So this would be the case where f double prime at c is positive. Then that has to be a local minimum. Likewise, if you have a critical value and f double prime is less than 0, so the graph is concave down. So that would look like that. You'd still have your derivative as 0 there, but also the derivative is negative there, so it's concave down. So that has to be a local max. All right. What our last example is going to be is to just discuss this curve. And by discuss, I mean we're going to completely sketch it out. We're going to find all its intervals of increasing or decreasing. And we won't even have to use our calculator. So, y equals x to the fourth minus 4x cubed. How do I want to do this? Stupid, I should have put in a blank page at the end of this. All right, I'm just going to have to try and be really conscious of my use of space. All right, let's do a little algebra stuff. We can find some important characteristics without using calculus. So first, let's find the zeros if we can. So x to the fourth minus 4x cubed. So I'm just going to set it equal to 0. I can factor out x cubed. I then have x minus 4. So x equals 0 and 4 is what I get. These are just zeros of the graph. That doesn't look right. Does 0 have an e at the end of it? All right, here's what I'm going to do to avoid that. I'm going to call them roots. Okay. So, all right, let's put my function down here as I sketch it. All right, so far I know I have roots at 0, and I'll call this, I don't know, this is 4 right here. Boom. All right. Let's see. I can find the y-intercept too. And for that, I'll just plug in 0 for x, and we get y equals 0. So there's only one y-intercept. Great. The other thing, let's talk about end behavior. Now, I guess you don't, well, probably don't need calculus to know this because this is just a polynomial. You guys should know what's going on with polynomials in terms of the end behavior. Yeah, there's no e on the end of it, right? Okay. It's just zeros. That does look better. All right. Technically, when we're finding end behavior, we're taking the limit as x goes to positive and negative infinity, and you're kind of telling me what's going on with the function. So in this case, this is a polynomial of degree 4. So you know that the ends are either going to both be opening upwards or downwards because it's an even degreed polynomial. And then we know, well, the coefficient of the fourth power is positive, so the end behavior is such that the ends should both be going in the positive direction. So what I mean by that is it could be doing some interesting stuff in between, but I know that in the end it's going to, both ends have to end up facing upwards like that. So I'm just going to sketch that in to remind myself of that. So somewhere over here and somewhere over here, my ends are going to be pointing up, right? All right. So now let's start with increasing and decreasing intervals. Let's do some calculus here. So y prime is 4x cubed minus 12x squared. I'll set that equal to 0. I'll solve. So I can factor out a 4x squared from there. Sorry, I need to be a little bit more space conscious. So factor out 4x squared. What would I be left with? X minus 3. So I get two critical values. I get x equals 0 and 3. Let's place those on the number line. And what we want to look at is y prime in between those values. So I know that y prime is 0 at 0 and 3. In between those values, let's say I choose like -1. Do I get back a positive or a negative? Well, again, it's always probably easiest to look at the factored value. If I plug in -1 to 4x squared, I get positive. If I plug in -1 to x minus 3, I get negative. Positive times negative is negative. All right. Next interval between 0 and 3. Let's say we choose +1. This is positive. This is still negative, so still negative. And then let's choose, let's say 4. This is positive. This is positive. Positive times positive is positive. Great. So let's talk about intervals of increasing or decreasing. Our function will increase on one interval, 3 to infinity, and it will decrease on negative 1, no, not negative 1, I'm sorry, negative infinity to 0, and from 0 to 3. Yes, you could just state, I'd fine if you just state that it's completely decreasing from negative infinity to 3. I'm just pointing out there is something going on at 0 that we're going to be interested in, but it's not a maximum or a minimum. All right. So with that, we can now find our local max and minimum. So our function goes from decreasing to having a slope of 0 to decreasing, so there's neither at 0, but at 3 it goes from decreasing, so negative slopes, to increasing, positive slopes, so that has to be the location of a local minimum value. And so I have a local minimum at 3 something. To figure out what it is, I can plug in 3 to my original function, so y of 3, so that's 3 to the 4th minus 4 times 3 cubed, which is what, 81 minus, oh boy, it's 4 times 3 cubed, 81 minus 4 times 3 to the 3rd. All right, so I get negative 27 is what this comes out to. All right, so I have a local minimum at 3, negative 27. And there are no local maximum, does not exist. Okay. So the last thing to check for is concavity. I'm going to do this real quick. So that's going to be the second derivative. So I'm going to look at y double prime. So the second derivative is going to be 12x squared minus 24x. It's the same process that we used to find the local maximum and minimum. It's just now we're doing this with the second derivative instead of with the first derivative. So I'm going to take that, I'm going to set it equal to 0. I'm going to solve. So let's factor out 12x, we get times x minus 2. So we get these two sort of critical numbers of the second derivative. We get 0 and 2. And then I'm going to do what I did with the first derivative. I'm going to plot them on a number line. But now what I'm interested in is knowing the value of the second derivative. I want to know where it's positive or negative. So I'm going to do the same thing. I'll just test values on that number line in between those critical values. So let's take like negative 1. If I plug that into my second derivative, I get negative times negative, which is positive. Plug in positive 1. I get positive times negative, which is negative. Let's plug in 3. I get positive times positive, which is positive. And so the second derivative tells me about concavity. So I have concave up when it's positive and concave down when it's negative. So my graph is concave up from negative infinity to 0 and from 2 to infinity. It's positive. The second derivative is positive there. And it's concave down from 0 to 2. So there's a change in concavity at 2, which means there must be an inflection point at 2. So there's an inflection point at 2, and I'm just going to plug 2 into my original function to get that inflection point. So y of 2 is 2 to the 4th minus 4 times 2 cubed, which is negative 16. All right, so putting it all together. We have a local minimum at 3, negative 27. We'll put, let's say that's 3. I'll say negative 27 is right there. Boom, there's my local minimum. But then I'm also going to have this inflection point at 2, negative 16. Let's say that's right there. My function is decreasing from negative infinity to 0 and from 0 to 3. And it's concave down from negative infinity to 0 and from 2 to infinity. Sorry, there's another inflection point at 0, 0. I just recognized that. So concave up. So it's going to be concave up over here, just slightly. Then it's going to change to concave down and decreasing to that point of inflection. And then it's back to concave up for the rest of the way. So this is all concave up out to infinity. So like that. So that's what our graph will look like. All right.